The world of technology is on the brink of a new era. A revolution is brewing, promising to transform the very fabric of how we process information and solve complex problems. This revolution is quantum computing, a paradigm shift from traditional computing methods. Imagine a world where scientific breakthroughs occur at an unprecedented pace, where diseases are understood and treated with remarkable precision, and where the limitations of current computational power become a distant memory. This is the promise of quantum computing. No longer a concept confined to science fiction, quantum computing is rapidly moving from theoretical research to tangible reality. Companies like PsiQuantum, a California-based startup, are at the forefront of this revolution. Inside laboratories humming with cutting-edge technology, researchers are working tirelessly to build the world's first practical quantum computers. These machines, operating at temperatures colder than deep space, hold the potential to unlock solutions to problems that have long stumped even the most powerful supercomputers. The race is on, with tech giants like Google, Microsoft, Amazon and IBM investing heavily in quantum research and development. Governments around the globe recognize the transformative potential of quantum computing, pouring billions of dollars into research initiatives and fostering collaborations between academia and industry. The excitement surrounding quantum computing is palpable, fueled by recent breakthroughs and the promise of a future brimming with possibilities. Investors too have taken notice, with quantum computing stocks soaring as they bet on the companies poised to lead this technological revolution. But what exactly is quantum computing? How does it differ from the computers we use every day? And how close are we to realizing its full potential? To understand the transformative power of quantum computing, we need to delve into the strange and counterintuitive world of quantum mechanics. Unlike classical computers, which rely on bits to represent information as zeros or ones, quantum computers harness the bizarre properties of quantum bits, or qubits. Qubits can exist in a state of superposition, meaning they can be both 0 and 1 simultaneously. This mind-bending concept, along with another quantum phenomenon called entanglement, allows quantum computers to perform calculations in ways that defy classical logic. Entanglement links two or more qubits in such a way that they become interconnected, even if separated by vast distances. Any change to one entangled qubit instantly affects the others, regardless of physical separation. These unique quantum properties give quantum computers an exponential advantage over classical computers when tackling certain types of problems. Imagine searching through a vast maze. A classical computer would have to explore each path sequentially until it found the exit. A quantum computer leveraging superposition could explore all paths simultaneously, finding the solution exponentially faster. This ability to explore multiple possibilities at once makes quantum computers ideally suited for tackling complex problems in fields like medicine, materials science, and artificial intelligence. Imagine designing new drugs with unparalleled precision, developing revolutionary materials with tailored properties, or creating artificial intelligence that surpasses human capabilities. These are just a few glimpses into the transformative potential of quantum computing, a potential that is closer than we might think. Imagine a coin spinning in the air, suspended between heads and tails. Until it lands, it exists in both states simultaneously. This is a simplified analogy for the quantum phenomenon known as superposition. In the quantum realm, particles like atoms and photons don't conform to the rigid rules of the macroscopic world. They exist in a haze of probabilities, occupying multiple states at once. This concept, as mind-boggling as it may seem, is the bedrock of quantum computing. At the heart of a quantum computer lies the qubit, the quantum equivalent of a classical bit. While a classical bit can only be either a 0 or a 1, a qubit can exist in a superposition of both states concurrently. This fundamental difference is what grants quantum computers their extraordinary power. Think of a classical computer as a solo musician playing one note at a time. A quantum computer with its qubits in superposition is like a grand orchestra capable of playing a symphony of notes simultaneously. This parallelism allows quantum computers to explore a vast number of possibilities at once, dramatically accelerating certain computations that would take classical computers an impractical amount of time. This power of superposition is not merely a theoretical curiosity. It has profound implications for solving real-world problems. Consider the challenge of drug discovery, where researchers must sift through countless molecular combinations to identify potential drug candidates. A quantum computer, leveraging superposition, could explore these combinations simultaneously, significantly speeding up the process and potentially leading to the development of life-saving treatments. If superposition is the heart of quantum computing, then entanglement is its soul. Entanglement is a bizarre and captivating phenomenon where two or more quantum particles become linked even if separated by vast distances. Imagine two coins flipping in perfect unison no matter how far apart they are. This interconnectedness, defying our classical intuition, is the essence of entanglement. When two qubits become entangled, their fates are intertwined. Measuring the state of one qubit instantly reveals the state of the other, regardless of the physical distance between them. This instantaneous connection, seemingly faster than the speed of light, has puzzled physicists for decades. In the realm of quantum computing, entanglement is a powerful resource. It allows for the creation of complex correlations between qubits, enabling quantum computers to tackle problems that involve intricate relationships and dependencies. This interconnectedness is particularly valuable in fields like materials science, where understanding the behavior of electrons within a material is crucial for designing new materials with desired properties. Entanglement also plays a crucial role in quantum communication and cryptography. The secure transmission of information is paramount in today's digital age, and entanglement offers a way to transmit data with unparalleled security. By encoding information in the entangled states of qubits, it becomes impossible for eavesdroppers to intercept the data without disturbing the entanglement, alerting the intended recipient to the breach. Section 3. Beyond classical computation, the combined power of superposition and entanglement allows quantum computers to transcend the limitations of classical computing. Problems that would take classical computers billions of years to solve could potentially be tackled by quantum computers in a matter of hours or even minutes. This paradigm shift in computational power has the potential to revolutionize countless industries. In finance, quantum computers could be used to develop more sophisticated risk management models, optimize investment portfolios, and detect fraudulent transactions with unprecedented accuracy. The ability to analyze vast data sets and identify patterns that would elude classical algorithms could give financial institutions a significant edge in the market. In materials science, quantum computers could accelerate the discovery and development of new materials with tailored properties. From lighter and more durable materials for aerospace applications to more efficient solar cells for renewable energy, the possibilities are vast. By simulating the behavior of molecules and atoms at the quantum level, researchers could design materials with unprecedented precision, leading to breakthroughs in fields ranging from energy to medicine. The impact of quantum computing on artificial intelligence is equally profound. Quantum machine learning algorithms have the potential to revolutionize how we train and deploy AI models. By leveraging the power of superposition and entanglement, quantum computers could analyze massive data sets and identify complex patterns far more efficiently than classical computers, leading to the development of more sophisticated and capable AI systems. Section 1. Pioneering the quantum frontier. The race to build a practical quantum computer has ignited a global pursuit, with research teams around the world pushing the boundaries of what's possible. Among these pioneers is PsiQuantum, a California-based startup that has captured the attention of investors and industry leaders alike. PsiQuantum's approach to quantum computing centers around photonic qubits, which utilize particles of light or photons to store and process information. Unlike other qubit technologies that require extremely low temperatures to operate, photonic qubits can function at room temperature, making them potentially more practical for real-world applications. PsiQuantum's vision extends beyond building a single isolated quantum computer. The company envisions a future where quantum computers are integrated into existing data centers, seamlessly connecting with classical computing infrastructure. This approach aims to bridge the gap between the theoretical potential of quantum computing and its practical implementation in real-world settings. PsiQuantum's ambitious roadmap has attracted significant investment from both the private and public sectors, including a major partnership with the Australian government to build a utility-scale quantum computer in Brisbane. This collaboration underscores the growing global recognition of quantum computing's transformative potential and the importance of fostering international partnerships to accelerate its development. PsiQuantum's journey is just one example of the many paths being explored in the quest for quantum supremacy. From superconducting qubits to trapped ions and neutral atoms, each qubit technology comes with its own set of advantages and challenges. The diversity of approaches reflects the complexity of quantum computing and the need for continued exploration and innovation to overcome the remaining hurdles on the path to building a truly practical and scalable quantum computer. Section 2. The Quest for Qubit Supremacy. In the realm of quantum computing, the pursuit of quantum supremacy represents a pivotal milestone. This coveted achievement signifies the moment when a quantum computer can outperform even the most powerful classical supercomputers in solving a specific computational task. Google made headlines in 2019 when it claimed to have achieved quantum supremacy with its Sycamore processor, which reportedly performed a complex calculation in a matter of minutes that would have taken a classical supercomputer thousands of years. While Google's achievement was met with both excitement and skepticism, it marked a significant step forward in the field, demonstrating the potential of quantum computers to tackle problems previously considered intractable. However, the quest for quantum supremacy is not solely about achieving faster computation. It's about unlocking the ability to solve problems that are fundamentally beyond the reach of classical computers. Problems that could hold the key to breakthroughs in medicine, materials, science, and artificial intelligence. The race to build more powerful and reliable quantum computers is driven by the tantalizing prospect of achieving quantum advantage, a stage where quantum computers can provide a significant speed-up or cost reduction for solving real-world problems. This milestone, while still some years away, holds the promise of revolutionizing industries and transforming our world in profound ways. As the number of qubits in quantum computers continues to increase and error rates decrease, we move closer to the era of quantum advantage. This era will be marked by the development of quantum algorithms and applications that leverage the unique capabilities of quantum computers to solve problems that have long plagued humanity. From designing new drugs and materials to optimizing complex logistics and financial systems, the potential applications of quantum computing are vast and transformative. PsiQuantum's approach to quantum computing stands out for its reliance on photonic qubits, a technology that harnesses the power of light to store and process information. Photons, the fundamental particles of light, are remarkably stable and resistant to environmental noise, making them ideal candidates for building reliable qubits. Unlike other qubit technologies that require extremely low temperatures to operate, photonic qubits can function at room temperature, significantly simplifying the engineering challenges associated with building and scaling quantum computers. PsiQuantum's photonic chips are manufactured using standard semiconductor fabrication techniques, leveraging the decades of investment and innovation in the semiconductor industry. This approach allows PsiQuantum to tap into existing manufacturing capabilities, potentially accelerating the development and deployment of its quantum computers. By integrating photonic chips with conventional silicon-based electronics, PsiQuantum aims to create hybrid quantum classical systems that can seamlessly integrate with existing data centers and computing infrastructure. This hybrid approach leverages the strengths of both classical and quantum computing, allowing for a more gradual transition to a quantum-powered future. PsiQuantum's vision extends beyond building a single monolithic quantum computer. The company envisions a future where quantum computers are interconnected, forming a global network capable of tackling humanity's most daunting computational challenges. This interconnected network of quantum computers, operating in concert with classical computing systems, could unlock unprecedented capabilities in fields ranging from drug discovery and materials science to artificial intelligence and climate modeling. The symphony of light and silicon, orchestrated by Quantum and other pioneers in the field, holds the promise of a future where the boundaries of computation are redefined and the impossible becomes possible. As the field of quantum computing rapidly advances, a critical challenge emerges: the scarcity of qualified individuals with the expertise to design, build, and operate these complex systems. The quantum talent gap is a growing concern for industry leaders and researchers alike, as the demand for skilled professionals far outpaces the current supply. Universities and research institutions are working diligently to develop specialized quantum computing programs to equip the next generation of scientists and engineers with the necessary skills. However, building a robust quantum workforce will require a concerted effort from academia, industry, and governments. One promising approach involves fostering closer collaboration between these stakeholders to create apprenticeship programs, internships, and other opportunities for hands-on experience with quantum computing technologies. Another strategy involves leveraging online learning platforms and other innovative educational tools to make quantum computing knowledge more accessible to a wider audience. By demystifying this complex field and providing engaging learning experiences, we can inspire a new generation of quantum enthusiasts and equip them with the skills to thrive in this rapidly evolving industry. Bridging the quantum talent gap is not just about filling job openings, it's about fostering a vibrant and diverse quantum ecosystem. By attracting individuals from a wide range of backgrounds and disciplines, we can cultivate a culture of innovation and collaboration that will drive the field forward and unlock the full potential of quantum computing for the benefit of humanity. The very essence of quantum computing's power, its ability to dance in the realm of superposition and entanglement, also makes it incredibly susceptible to the slightest disturbances from the outside world. Imagine a delicate soap bubble shimmering with iridescent colors but prone to bursting at the slightest touch. Such is the delicate nature of qubits, the building blocks of quantum computers. Unlike the robust bits of classical computers, which are physically etched into silicon chips, qubits exist in a fragile state of quantum superposition, easily perturbed by environmental noise. The slightest fluctuations in temperature, stray electromagnetic fields, or even the faintest vibrations can disrupt this delicate balance, causing qubits to lose their quantum properties and collapse into a classical state. This phenomenon, known as decoherence, is the bane of quantum engineers, representing a formidable hurdle in the quest to build practical and reliable quantum computers. To protect these fragile qubits from the ravages of decoherence, researchers have devised ingenious techniques to isolate them from the outside world. One common approach involves cooling qubits to ultra-low temperatures, just a fraction of a degree above absolute zero. At these frigid temperatures, atoms and electrons move sluggishly, minimizing thermal vibrations that can disrupt qubit coherence. Imagine a bustling city street transformed into a serene winter wonderland, the hustle and bustle replaced by a tranquil stillness. Another technique involves shielding qubits from stray electromagnetic fields by encasing them in superconducting materials that expel magnetic fields. These superconducting shields act like quantum fortresses, protecting the delicate qubits from the disruptive influences of the outside world. Despite these protective measures, decoherence remains a persistent challenge, limiting the amount of time qubits can maintain their quantum states and perform computations. Section 2. The Error of Our Ways, Quantum Decoherence. Quantum decoherence, the Achilles heel of quantum computing, arises from the inevitable interaction between qubits and their environment. Imagine a drop of ink diffusing in a glass of water, its boundaries blurring as it interacts with the surrounding molecules. Similarly, qubits, when exposed to environmental noise, gradually lose their quantum coherence, their delicate superposition states collapsing into classical certainty. This loss of coherence introduces errors into quantum computations, undermining the accuracy and reliability of quantum computers. To combat these errors, quantum engineers have developed sophisticated error correction techniques akin to digital spell checkers for quantum computations. These techniques involve encoding quantum information redundantly across multiple physical qubits, creating a protective web of entanglement that can detect and correct errors. Imagine a group of skilled dancers moving in perfect synchrony, able to compensate for a misstep by a single dancer without disrupting the overall harmony of the performance. Quantum error correction is a complex and resource-intensive process, requiring a significant overhead in the number of physical qubits needed to encode a single logical qubit. Despite these challenges, significant progress has been made in developing and implementing error correction codes, paving the way for more reliable and fault-tolerant quantum computers. As quantum computers continue to scale in size and complexity, the development of robust error correction techniques will be crucial for unlocking their full potential. Just as a symphony orchestra relies on the precision and coordination of its musicians to create a harmonious masterpiece, so too will future quantum computers depend on the reliability and accuracy of their error correction mechanisms to perform complex computations with fidelity and precision. Section 3. Engineering the Quantum Future, a Multifaceted Approach. The pursuit of a practical and scalable quantum computer is not a monolithic endeavor, but rather a multifaceted exploration of diverse technological avenues. Each approach to building a quantum computer comes with its own set of strengths and weaknesses, requiring a careful balancing act between qubit stability, controllability, and scalability. Imagine a team of architects and engineers designing a futuristic city, each contributing their unique expertise to create a harmonious blend of form and function. Superconducting qubits, one of the most mature qubit technologies, rely on tiny electrical circuits cooled to ultra-low temperatures to exhibit quantum behavior. These circuits, fabricated using well-established semiconductor manufacturing techniques, offer high fidelity and controllability, but require complex and expensive cryogenic systems to operate. Trapped ion qubits, on the other hand, leverage individual atoms suspended in electric fields, offering exceptional coherence times, but presenting challenges in scalability and control. Neutral atom qubits, another promising approach, use lasers to trap and manipulate neutral atoms, offering a balance between coherence and scalability. Photonic qubits, championed by companies like PsiQuantum, utilize particles of light or photons to store and process information, offering the advantage of room temperature operation but presenting challenges in qubit interaction and scalability. Each of these qubit technologies represents a different path on the roadmap to quantum computing, each with its own set of milestones and hurdles to overcome. The diversity of approaches reflects the dynamism of the field, with researchers constantly pushing the boundaries of what's possible. As the field matures, it's likely that a hybrid approach combining the strengths of different qubit technologies will emerge as the most viable path to building a truly practical and scalable quantum computer. This hybrid approach, akin to a symphony orchestra combining the unique sounds of different instruments, will leverage the strengths of each qubit technology to create a harmonious and powerful computational symphony. Section 4. The Workforce Conundrum: Cultivating Quantum Expertise. The rapid advancement of quantum computing has unveiled a critical bottleneck on the path to widespread adoption: the acute shortage of skilled professionals equipped to navigate this complex and rapidly evolving field. The quantum workforce gap is a growing concern for industry leaders and policymakers alike, as the demand for quantum expertise far outstrips the current supply. Imagine a world on the cusp of a transportation revolution, with self-driving cars poised to transform our roads, but lacking a sufficient number of trained mechanics and engineers to maintain and repair these complex vehicles. Addressing this skills gap requires a multi-pronged approach involving collaboration between academia, industry, and governments. Universities and research institutions are at the forefront of cultivating the next generation of quantum experts, developing specialized quantum computing programs to equip students with the necessary theoretical and practical skills. However, traditional academic pathways alone are insufficient to meet the growing demand. Industry partnerships and apprenticeship programs are crucial for bridging the gap between theoretical knowledge and real-world applications. By providing students with hands-on experience working with cutting-edge quantum technologies, these programs can foster a new generation of quantum-ready professionals. Governments also have a vital role to play, providing funding for research and development, incentivizing private sector investment in quantum technologies, and supporting workforce training initiatives. Bridging the quantum workforce gap is not just about filling job openings, it's about cultivating a thriving and diverse quantum ecosystem. By attracting individuals from a wide range of backgrounds and disciplines, we can foster a culture of innovation and collaboration that will propel the field forward. Just as a symphony orchestra draws on the talents of musicians from diverse backgrounds to create a harmonious and captivating performance, so too will the quantum computing revolution require a diverse and skilled workforce to unlock its full potential and orchestrate a brighter future for humanity. Imagine a world where scientists could design life-saving drugs with pinpoint accuracy, tailoring treatments to an individual's genetic makeup and eradicating diseases at their molecular roots. This vision, once confined to the realm of science fiction, is inching closer to reality thanks to the transformative potential of quantum computing in the field of quantum chemistry. At the heart of this revolution lies the ability of quantum computers to simulate the intricate dance of molecules and atoms, a feat that remains beyond the reach of even the most powerful classical computers. Classical computers struggle to model the complex interactions between electrons that govern chemical reactions and material properties. These interactions, governed by the laws of quantum mechanics, involve a mind-boggling number of variables and possibilities, quickly overwhelming the computational capabilities of classical systems. Quantum computers, on the other hand, are uniquely suited to tackle these challenges. Their ability to leverage superposition and entanglement allows them to explore multiple quantum states simultaneously, effectively mimicking the parallel nature of chemical reactions. This capability opens up a world of possibilities for drug discovery and material science. Quantum computers could enable researchers to design new drugs with unprecedented precision, predicting their efficacy and potential side effects with remarkable accuracy. This could significantly accelerate the drug development process, bringing life-saving treatments to patients faster and at a lower cost. In materials science, quantum simulations could lead to the discovery of new materials with tailored properties, revolutionizing industries ranging from energy to electronics. Imagine solar cells with dramatically increased efficiency batteries, with significantly higher capacity or lighter and stronger materials for aerospace applications. These are just a few glimpses into the transformative potential of quantum chemistry, a field poised to redefine our understanding of the molecular world and unlock a new era of scientific innovation. The world of finance, built on a foundation of complex algorithms, intricate risk models, and vast datasets, is ripe for disruption by the transformative power of quantum computing. Imagine financial institutions equipped with the ability to make lightning-fast trading decisions, optimize investment portfolios with unparalleled precision, and detect fraudulent activities with uncanny accuracy. This is not a scene from a futuristic thriller, it's a glimpse into the future of finance, powered by the quantum revolution. Quantum computers, with their ability to explore multiple possibilities simultaneously, excel at tackling optimization problems that plague classical financial models. Consider the challenge of portfolio optimization, where the goal is to allocate assets in a way that maximizes returns while minimizing risk. Classical algorithms struggle to find the optimal solution among the astronomical number of possible combinations, especially as the number of assets and constraints grows. Quantum algorithms, on the other hand, can navigate this complex landscape with remarkable efficiency, leveraging superposition to explore multiple investment strategies concurrently and identify the optimal portfolio allocation with unprecedented speed and accuracy. This capability could give financial institutions a significant edge in the market, allowing them to make more informed investment decisions and potentially generate higher returns for their clients. Beyond portfolio optimization, quantum computing holds promise for revolutionizing other areas of finance, including risk management, fraud detection, and derivative pricing. Quantum algorithms could enable financial institutions to develop more sophisticated risk models, identify fraudulent transactions with greater accuracy, and price complex financial instruments with greater speed and precision. The financial industry, long a hotbed of technological innovation, is poised for a quantum leap forward, driven by the promise of unprecedented insights and competitive advantage. In a world grappling with increasingly complex supply chains, intricate transportation networks, and a growing need for efficiency, quantum computing emerges as a beacon of hope, promising to optimize logistics and streamline operations in ways unimaginable with classical computers. Imagine a world where goods flow seamlessly from manufacturers to consumers. Traffic congestion becomes a distant memory, and resource allocation is optimized to minimize waste and maximize sustainability. This is the vision of a quantum-powered future, where the ability of quantum computers to tackle complex optimization problems unlocks unprecedented levels of efficiency and productivity across industries. At the heart of this transformation lies the ability of quantum algorithms to explore a vast number of possibilities, simultaneously finding the optimal solution among a sea of options that would overwhelm even the most powerful classical computers. Consider the challenge of route optimization, where the goal is to find the most efficient path for a delivery truck to navigate a complex network of roads, accounting for traffic conditions, delivery windows, and fuel efficiency. Classical algorithms struggle to find the optimal solution as the number of variables and constraints grows, often resorting to approximations that result in suboptimal routes and wasted resources. Quantum algorithms, on the other hand, excel at navigating these complex optimization landscapes. By leveraging superposition, quantum computers can explore multiple routes concurrently, evaluating their efficiency based on real-time data and identifying the optimal path that minimizes travel time, fuel consumption, and delivery costs. This capability has the potential to revolutionize logistics and transportation, leading to faster delivery times, reduced fuel consumption, and a more sustainable and efficient global supply chain. Section 4. Accelerating Artificial Intelligence with Quantum Power. The field of artificial intelligence, poised to revolutionize industries and reshape our world, stands to gain immensely from the computational prowess of quantum computers. Imagine AI systems capable of learning from massive datasets with unprecedented speed, recognizing complex patterns that elude classical algorithms, and making decisions with human-like intuition. This is the promise of quantum-enhanced AI, a convergence of two transformative technologies with the potential to unlock unprecedented capabilities. Quantum machine learning, a burgeoning field at the intersection of quantum computing and AI, explores the use of quantum algorithms to enhance the performance of machine learning models. Classical machine learning algorithms, while powerful, often struggle to handle the massive datasets and complex patterns found in real-world applications. Quantum machine learning algorithms, on the other hand, leverage superposition and entanglement to explore a vast number of possibilities simultaneously, identifying patterns and making connections that would remain hidden from classical algorithms. This capability could lead to the development of more sophisticated and capable AI systems, capable of tackling challenges ranging from drug discovery and material science to natural language processing and image recognition. Quantum computers could also accelerate the training process for AI models, which often require vast amounts of data and computational resources. By leveraging their inherent parallelism, quantum computers could significantly reduce the time and cost associated with training AI models, making it feasible to develop and deploy more sophisticated AI applications across a wider range of industries. The convergence of quantum computing and artificial intelligence holds immense promise for unlocking a new era of intelligent systems, capable of solving some of humanity's most pressing challenges. Section 5. Cultivating quantum literacy, preparing for a quantum future. As quantum computing transitions from the realm of scientific research to real-world applications, a critical need emerges to cultivate a society equipped with the knowledge and skills to navigate this transformative technology. Quantum literacy, the ability to grasp the fundamental concepts of quantum mechanics and their implications for quantum computing, will be essential for individuals, businesses, and governments to thrive in a quantum-powered future. This is not about turning everyone into quantum physicists. It's about fostering a basic understanding of how quantum computers work, their potential applications, and their limitations. Just as computer literacy became essential in the digital age, quantum literacy will be crucial for navigating the opportunities and challenges of the quantum era. Educating the next generation about quantum computing is paramount. Integrating quantum concepts into science, technology, engineering, and mathematics curricula at all levels of education will be crucial for sparking curiosity and preparing students for future careers in this rapidly evolving field. Beyond formal education, accessible and engaging resources such as online courses, public lectures, and interactive museums can play a vital role in demystifying quantum computing and making it accessible to a wider audience. Cultivating quantum literacy is not just about technical knowledge. It's about fostering a societal understanding of the potential benefits and ethical considerations associated with this transformative technology. As quantum computers become more powerful, it's crucial to engage in thoughtful discussions about their potential impact on society, addressing concerns about job displacement, data security, and the potential for misuse. By promoting responsible innovation and fostering a dialogue between experts and the public, we can ensure that the quantum revolution benefits all of humanity. The race to build a practical quantum computer has sparked an unprecedented wave of investment, with governments, venture capitalists, and tech giants pouring billions of dollars into research and development. This global surge in funding reflects the widespread recognition of quantum computing's transformative potential and the belief that early investments will yield significant economic and strategic advantages in the years to come. Imagine a gold rush, not for a precious metal, but for a technology that promises to unlock untold computational riches. Governments around the world are leading the charge, recognizing that quantum computing is not just a scientific endeavor, but a strategic imperative with national security and economic implications. The United States, China, and the European Union have all launched ambitious quantum initiatives, funding research, fostering collaboration between academia and industry, and developing national quantum strategies to guide their investments and ensure their competitiveness in the global quantum race. Venture capitalists, always on the lookout for disruptive technologies, have also jumped on the quantum bandwagon, pouring billions into promising quantum startups and fueling the growth of a vibrant quantum ecosystem. These early-stage investments are crucial for nurturing innovation and accelerating the development of quantum hardware, software, and applications. Tech giants, not wanting to be left behind in the quantum gold rush, are also making significant investments, establishing their own quantum research labs, acquiring quantum startups, and forming strategic partnerships to secure their place in the quantum future. The convergence of government funding, venture capital, and corporate investment has created a fertile ground for quantum innovation, accelerating the pace of discovery and pushing the boundaries of what's possible. Then the economic potential of quantum computing is staggering, with analysts predicting that it will unlock trillions of dollars in value across industries over the next few decades. Imagine a world where quantum computers accelerate drug discovery, leading to the development of new treatments for currently incurable diseases. Imagine material scientists designing revolutionary materials with tailored properties, revolutionizing industries ranging from energy to electronics. Imagine financial institutions using quantum algorithms to make lightning-fast trading decisions and manage risk with unprecedented accuracy. These are just a few glimpses into the transformative potential of quantum computing, a technology poised to reshape industries and create entirely new economic sectors. The healthcare industry stands to benefit immensely from quantum computing, with applications ranging from drug discovery and personalized medicine to medical imaging and diagnostics. Quantum simulations could accelerate the development of new drugs and therapies, potentially leading to breakthroughs in the treatment of cancer, Alzheimer's disease, and other debilitating conditions. The materials science industry is another prime candidate for disruption by quantum computing. Quantum simulations could enable scientists to design new materials with tailored properties such as enhanced strength, conductivity, or durability. These advances could revolutionize industries ranging from aerospace and automotive to energy and electronics, leading to the development of lighter and more fuel-efficient vehicles, more powerful and longer-lasting batteries, and more efficient solar cells. The financial services industry, long a hotbed of technological innovation, is also poised for a quantum leap forward. Quantum algorithms could enable financial institutions to develop more sophisticated risk models, optimize investment portfolios with greater accuracy, and detect fraudulent transactions with greater speed and precision. The potential for quantum computing to transform industries is vast, and the race is on to harness its power and unlock its economic potential. The excitement surrounding quantum computing is palpable, fueled by breathless media headlines, soaring stock prices, and bold predictions of a quantum future just around the corner. While the potential of quantum computing is undeniable, it's crucial to navigate the hype cycle with a healthy dose of realism, recognizing that the path to widespread adoption will be marked by both triumphs and setbacks. Imagine a mountain climber scaling a treacherous peak, inspired by the breathtaking view from the summit, but mindful of the challenges and dangers along the way. Quantum computing is still in its early stages of development, and significant technical hurdles remain before it can deliver on its transformative promises. Building and scaling quantum computers is a formidable engineering challenge, requiring breakthroughs in qubit stability, error correction, and control systems. Developing quantum algorithms that outperform classical algorithms for real-world problems is another major challenge, requiring a deep understanding of both quantum mechanics and the specific domain of application. While some industry observers predict that quantum computing will revolutionize industries within the next few years, others caution that widespread adoption is still decades away. The reality is likely to fall somewhere in between, with certain quantum applications, such as materials discovery optimization problems, reaching maturity sooner than others, such as drug discovery and cryptography. Navigating the hype cycle requires a balanced perspective, acknowledging both the transformative potential of quantum computing and the significant challenges that lie ahead. By focusing on long-term progress, supporting fundamental research, and fostering collaboration between academia, industry, and governments, we can ensure that the quantum revolution delivers on its promises and benefits all of humanity. The journey into the quantum realm is not for the faint of heart. It is a journey fraught with challenges, setbacks, and the daunting task of unraveling the mysteries of a reality that often defies our everyday intuition. Yet it is precisely this journey, this relentless pursuit of understanding and harnessing the bizarre yet beautiful laws of quantum mechanics, that holds the key to unlocking a future of limitless potential. Quantum computing, once a distant dream confined to the pages of science fiction, is now a tangible reality, a testament to human ingenuity and our insatiable thirst for knowledge. While the path ahead is not without its obstacles, the progress made in recent years has been nothing short of remarkable. From the first rudimentary qubits to the increasingly sophisticated quantum computers being developed in labs around the world, we are witnessing the birth of a new era of computation, one that promises to redefine the boundaries of what's possible. Imagine a world where diseases are eradicated at their molecular roots, where new materials with unimaginable properties revolutionize industries, and where the complexities of the universe are simulated with unprecedented accuracy. This is the promise of the quantum horizon. a future where the impossible becomes possible. The journey will be long and the challenges will be many, but the rewards are too great to ignore. By embracing the power of quantum computing, by fostering collaboration between brilliant minds across disciplines, and by nurturing a society equipped with the knowledge and skills to navigate this transformative technology, we can unlock a future where the limitations of today become the breakthroughs of tomorrow. The quantum revolution is not just about building faster computers, it's about expanding the frontiers of human knowledge, solving some of our most pressing global challenges, and creating a future where the power of quantum mechanics is harnessed for the benefit of all humankind. As we stand on the cusp of this new era, let us proceed with both excitement and a deep sense of responsibility, ensuring that the quantum future we create is one that reflects our shared values of progress, sustainability, and the betterment of humanity.